So hello everyone. Today we are going to model and analyze Couette flow under zero pressure gradient using ANSYS FLUENT software. So on hearing the word Couette flow, the first question that comes to our mind is what might be a Couette flow? What type of flow is a Couette flow? So here we can see that in fluid dynamics, Couette flow is a flow of a viscous fluid in a space between two surfaces, one of which is moving tangentially relative to the other. It means that there are two surfaces that are being separated by some distance, and any one of the surface has a positive or has a relative velocity with respect to the other surface. So basically we would be considering a pipe of length 500 mm which has a radius of 10 mm, and we will carry on with our analysis having a boundary condition such as the top wall has a velocity of 0.1 meter per second and bottom wall will be having a zero velocity because it would be static. We would be considering it to be static. So let's move to ANSYS workbench interface. So our domain of interest is fluid flow fluent. Let us create a standalone system. So fluid flow fluent. So these are the various parameters which we would be using. These are geometry, mesh, setup, solutions, and results. Geometry basically consists of the shape or the CAD file. Like for our case, we would be considering a pipe flow. So our geometry would basically represent or depict the pipe which we would be using for our analysis. Then comes meshing or mesh. So in meshing, like we can say meshing is a type of very important part in this analysis, because everything you do, it depends upon how good is your mesh, how you have optimized your mesh. So it's a very important parameter. We need to optimize in such a way that the computational time is very less, provided you obtain good and accurate or convergent solutions, experimental results. Then comes setup. So what we basically do in setup is that we select the various methods, or so we can change the characteristics of the fluids and all in this setup region. We can also apply the boundary conditions to our problem in this region. Then solution, self-explanatory, then that after applying the boundary conditions to the in the setup region, setup interface, we would run the calculation after initialization, and then we would obtain the solutions. Then we can go to the results and validate our experimental procedure. So let us start. Firstly, geometry. We would be considering a pipe of 500 mm length and a radius of 10 mm. So since design modular is basically used for it's used for 2D diagrams, so a cylinder that would be in 2D would represent a type of rectangle. So I would be using XY plane, preferably sketch 1, sketching. Okay, so since our units are in millimeter, so let me change it to millimeter from meter. Now we can zoom it. Okay, now rectangle, draw a rectangle here. Okay, now put on the dimensions. Our length is 500 mm and our breadth is 20 mm, or the breadth or the diameter, since the cross section would represent a rectangle. Okay, so let us zoom in and observe. So this is our domain of interest or domain of computation. Now we need to have concept, self surfaces from sketch. Let me select sketch 1, apply, surface, generate. So an appearance of grayish color would represent that your surface has been generated successfully. So now we are done with design modular interface. Let us close it. Okay, next we would be moving to meshing. Mesh is opening. Okay. Takes a bit time. Okay, so we obtained our pipe, or the cross section, longitudinal cross section of our pipe. So first step here, we need to generate the mesh. By default it will generate a mesh. Okay, the next step, let us insert a face meshing. Select this body, apply, generate mesh. Okay, now insert edge sizing. Now we need to have different numbers of elements in the 4 regions, or we can say these 2 regions would be having similar number of elements, and this would be having same. Now first let us consider this edge and this edge. Let me okay, apply. Okay, done. I would rather prefer number of divisions, since the dimension is quite orthogonal. Number of divisions, let me consider 500 number of divisions. For the other part, sizing this part and this part, apply, same number of divisions. Here select 50. Okay, so now let me generate the mesh. Yeah, so we can see that our mesh has been generated. Okay, so here we are having around 25,755 number of nodes in this entire arrangement, and we're having around 25,200 number of elements. Okay, so what we need to do next is that we need to name these regions, the 4 faces, for applying our boundary conditions. Basically this would be the bottom wall, which is stationary. Okay, this would be inlet. Done. Now this would be a domain of basically a domain of interest. So let us name it to be moving wall. Okay, and the last but not the least, quick name selection, let it name to be outlet. Okay, so we are done with the tasks that needs to be done in meshing interface. Now we can close it. So we can see here sign of thunderbolt. This is because even after the meshing has been done by the software, we have provided some changes. That is, we have named the 4 edges, so we need to update it in order to obtain a green tick. Okay, so we have obtained a green tick. Now next task would be moving to the setup. Select double precision and number of solver to be 4. It would be solving in 4 simultaneous regions, so device would face less problems while solving. Let the interface open properly. Okay, so we are solving a pressure based, steady, planar, absolute. There's nothing to be changed in this region. Models. we are using laminar model. Okay, the energy equations would be switched off because there is no point of using the energy equation in such type of fluid flow problem, because our main domain of interest is the relative velocity, which does not contains any type of parameters that would harm or impact the temperatures and all. So we won't be using energy equation in this solution. Now choosing the material, we would be selecting water, preferably water for our experiment, water liquid H2O. So copy, close, change, create, close. So you can see here the water liquid has been popped up. Next task, cell zone boundaries, cell zone conditions, surface boundary. Here we need to make sure that it's selected as water liquid. Okay, apply. Now the most importantly, the boundary conditions. The moving wall, the wall that has been moving. Okay, now just let me show you the parameters that I have been following. The top wall would be having a velocity of 0.1 meter per second. So it's a moving wall. Speed would be 0.1 meter, and by default the unit is meter per second. Okay, so moving wall, no slip condition, speed is 0.1 meter per second. Apply, close. For outlet, we can have pressure outlet. It's by default it's been provided here. Pressure outlet. Okay, apply, close. For inlet, we need to have pressure inlet. Apply, close. And the bottom wall, there is nothing to be changed in the bottom wall region. Everything is being like it needs to be kept as it is, stationary wall, it's not moving and no slip condition. Apply, close. So we're done with bottom wall, inlet, outlet and moving wall. Now the boundary conditions, we have done the tasks that those are related to boundary conditions. Now methods, scheme is coupled. Okay. And pressure, second order solvers for discretizing the pressure. Okay, so now monitors, residue. Here we can check that basically these are the this is the like criteria for convergence. After the error between two consecutive iterations for x velocity, y velocity or continuity reaches below 10 power minus 3, the solution or the system would provide me with a message that okay, the solution is being converged now. So I'm keeping it as it is. You can change it, no issues. As I've said already, because we need to optimize the time that is being required. So okay, initialize, we're doing hybrid initialization. Okay, run calculation, calculate. We can observe the ratings. This 10 power minus 6, 10 power minus 4, 10 power minus 3. Yeah, so we are being provided with a pop-up that our calculation has been completed. So this is the message or the symbol that the system has provided us, that okay, at 183rd iteration the solution has been converged. Now we are done with the solution. Okay, so basically we can obtain the graphs, we can obtain from this regions, or we can also go for post processing. We can obtain the velocity curves, contour. Yeah, so this is the velocity contour. can observe it. This region has a velocity of nearly 0.1 meter per second, and this region has a velocity, the boundary one, 0.1 meter per second. These regions have nearly zero velocities. Okay, close. Now we can also plot the okay, contours, plot xy plot for pressure, and this is basically an error. Need to change this plot directions. Save plot. Okay. Okay, so now let us move to post processing. We can close it. Yes, we can quit the application. Use settings changes for current and future calculations. Okay, now ANSYS would be closing the fluid flow setup. Okay, now we're done with solution. We would be moving towards the results or the post processing. So this is our domain of interest, as we have been doing from the past 10 to 15 minutes. So basically we are here to observe or see how the velocity or how the particles in this region would have the velocity due to like the velocity that would be nurtured of the particles between this region due to the movement of the upper plate. So first of all, let me put a streamline velocity. Okay, let it be ss1. Okay, so now we need to get it started from inlet velocity, number of points, just provide it to be 50. Apply. So we can obtain the velocity contour in this region or the streamlines. On zooming in, we can obtain the lines, basically the lines which represents the streamlines, the particles, the path followed by the fluid particles. Those generally represent the streamline. Okay, so basically by this contour or the streamline graph or the 3D view, we can validate the Couette's flow. One more thing that does need to be done. Streamline. Okay. Animation. Loop is provided to be 5. Save movie. What we are basically doing is we would be gathering or we would be like tracing the path followed by the velocity particles in these regions in real time. We would be observing that. Simple space 0.75 is good. JPG HD 720p is good. Okay, so this much is 40 frames is good. Okay, so we can see that these basically this circular particles represents the fluid particles. We can see that the velocity of the particles in the upper regions that are being depicted by red or yellowish colors move very fast due to the movement of the upper layer or the upper wall. This is quite 3D. This is explainable in a good manner that each and every particles that are being that move in this path can be like imagined how they actually move due to the presence of a shear region, have a shear region in the lower wall, and the upper wall being moving at certain velocity. So this validates our Couette's flow problem under zero pressure gradient. So let us pause it now. Okay, close. Okay, so basically we are done with this. Just let me uh, pressure streamline. Okay, it's fine. Okay, so these are done. Solution is done and the results we have obtained. Now we are updating the solution. Okay, so we are done with the problem. Geometry done, meshing done, setup, solution, results. We have shown here the velocity contours and the pressure variation in Couette flow. So these were our assumptions, and we can say this was a problem statement. These were the dimensions that we have considered during the onset of the problem, and these were the boundary conditions that were imposed by us. So we are done now. Thank you.